And so where we're at right now is we are combining all of our transformations together. This question is in function notation. It says, here is the original graph of f of x, and we want to sketch the graph of the following. The first thing I would do is I would move everything over. So I'll subtract 4 on both sides, and then label what each of the things are. So go from left to right, decide what's inside my function and what's outside of my function, because everything inside of the function is going to affect your x values. So when we get to this 1/2, that's inside our function, so it's going to be something horizontal. It's multiplying. This one's going to be a horizontal stretch. Underneath, remember, we always multiply by the reciprocal. So here, we would multiply our x values by -2. The next number we run into is the +1. We note this is nice. They have this already factored. Remember that special note that I suggested putting into your phone at 10 p.m. every night to remind you that, you haven't seen that on the video yet? Okay, to remind you that you always have to have it in factored form. So this one is already factored. You see that that 1/2 is outside, factored out of that x plus 1. So this +1 is going to be a horizontal translation. And what do we do with a +1? That will move 1 to the left. And finally, the -4 is a vertical translation. That will go 4 down. So first of all, we look at the equation. We make sure that it's in a proper form that we like. I like having that, moving that 4 over to the right-hand side, so y is right by itself. Then notice that it was already in factored form, labeled each of the things, and now we're ready to do the transformations. What we're going to do is we're going to look at our transformations for a couple of points. I know that they've labeled 2, 0.5, but can you see that you also have 1, 1 and -1, -1? Those seem to be even nicer values to work with. So I'm going to take my original points on my red graph as 1, 1 and -1, -1. I'm also going to note that on my original graph, I have an asymptote at x equals 0 and an asymptote at y equals 0. So I'm also going to write those down because I'm curious to see where do they end up. When you have multiple transformations, which we do in this situation, for your work, we're always going to do our, I'll just do the points, our stretches and compressions first, followed by our translations second. So above my first set of arrows, I'll list all of the stretches and compressions that happen in this transformation. Well, we only have one stretch. We have a horizontal stretch. Our x values are going to get multiplied by 2. So above these arrows, that's the only thing that's going to affect the first set of transformations. And then after we do our stretches and compressions, we do our translations, and we have 2 translations. We are going to go 1 to the left and 4 down. So what does that mean for our points? Well, my x values get multiplied by 2, so now I'm going to have 2, 1 and -2, -1. 1 to the left, we'll subtract 1 on each of those, so that'll be go down to 1 and down to -3. And 4 down, so if I'm at 1 and I go 4 down, I'm going to go to -3. I'm at -1 and I go 4 down, I'm going to go to -5. And finally, we're going to think about what happens to our asymptotes, because they're a key thing in this graph. What will their final equation be? Well, you'll find with asymptotes, because they start at 0, is multiplying the x or the y by anything ever going to affect something at 0? No. So the only thing that's going to affect your asymptotes at x equals 0 and y equals 0 is whether you move them left or right or up or down. Since we're moving 1 to the left, can you see that this asymptote, do it in red, is going to end up being 1 to the left at x equals -1. And this asymptote, y equals 0, the horizontal one, is only going to get affected if you move it up and down. Since we're going 4 down, it's going to end up at y equals -4. So we've taken a couple of points, and you can do more points if you want. If you want more accuracy, you can do more points. We've done a couple of points. The asymptotes are important. We saw where they ended up. Now we can go and take this and draw our final sketch. So I'll draw a new grid here. Start by drawing in your asymptotes. We're going to have an asymptote at x equals -1. We're going to have an asymptote at y equals -4. Plot our new points. So I have 1, -3. And label that point. And -3, -5. The shape has to stay the same. Important points to always label on your graph, if you can, are your x-intercepts and y-intercepts. So we were able to draw the graph with just those 2 key points. The question now is, could I label this point and this point? And how would I label those points if I wanted to be more accurate? Well, how do we find a y-intercept? You would plug in 0 for x. But what's the problem here is we only have function notation. We don't have an actual equation to figure out. So if I wanted to find both my x-intercept and y-intercept, I would need to know what the actual or explicit equation is that I'm dealing with. So the question is, do we recognize the graph that we started with? What's the actual equation of this graph? The actual equation would be 1 over x. So if the actual beginning equation was 1 over x, what is the equation? What did I have? F of 1/2 x plus 1 minus 4. How do I change the green graph in function notation to be explicit notation? Again, what is the idea of a function? Whatever's inside the function replaces x. So what do I have inside the function now? All of this is inside the function. So when I go to write the actual explicit equation, it's going to be 1 over, and instead of just 1 over x, I'm going to have 1 over 1/2 x plus 1. And then the minus 4 outside of the function stays outside of the function. So now that I have an explicit equation, now I could find my x-intercepts and y-intercepts if I wanted to. How do you find an x-intercept? Right? Make y equal to 0. How do you find a y-intercept? Make x equal to 0. Which of those two algebraically is easier to do? I think the second one. Because if you do the second one, let's do that one first. You'd have 1 over 1/2 0 plus 1 minus 4. And you just have to simplify dividing by a fraction is the same as multiplying by the reciprocal. So this would be 1 over 1 multiplied by 2 over 1, which is just 2 minus 4, negative 2. I'm going to go back to my graph after doing that math, and I can now make the dot big enough so it's exactly in the right spot. Say that I have 0, negative 2. That would be my y-intercept. Scroll back down if you were still writing that. If I wanted to find my x-intercept, that's plugging in 0 for y. Here it's a little bit more, right? We have 1/2 x plus 1 minus 4. How would I solve this equation? Move the 4 over to the other side. If your x is in your denominator and you're trying to solve, you have to multiply both sides to get rid of the stuff in your denominator. In this case, I would multiply both sides by 1/2 x plus 1 and this side by 1/2 x plus 1. That would simplify these on this side, leaving me with just 1. And on this side, 4 times 1/2 will be 2 times x plus 1. And now if you distribute, and solve, you get x is equal to negative 1/2. So it's using your skills from grade 11 with rational equations, solving for x from grade 9 and grade 10. And so we can go back to our graph and I can label that I know that this point is at negative 1/2, 0. So when we're graphing, we like to always have our asymptotes. The green points were 2 key points on our original graph. But then, whenever possible, also to label all of our intercepts, x-intercepts and y-intercepts. Now this question said, what was the domain and range of the original graph? Well, the domain was everything except it couldn't equal 0, and there was an asymptote for the range, so everything couldn't equal 0. Once we get to this green graph, our asymptotes have moved, and so now our domain is everything except for negative 1, and our range is everything except for negative 4. All right, so I'm going to give you a couple questions to work on. They were actually sponsored today, so that's nice.